Hello, everybody. So today we will cover chapter 4, and chapter 4 it's about time response. So there are some learning outcomes in this unit. So we need to learn how to use poles and zeros of a transfer function to determine the time response of a control system. So when we look into poles and zeros, it should be possible for us to find the time response of your control system. We need also to describe transient response of the first order system. We need to write the general response of a second order system given pole locations. I mean, you can say that we will divide systems into systems, which are first order system and higher order systems. And all higher order systems, we can represent it as a second order system because there is no big difference between the response of a third order and a second order system. So we can approximate the response of higher order systems as a second order system. So in this unit, we will study only the first order system and the response of the second order system given the pole location. When you are working with second order systems, there are some parameters. So we need to find the damping ratio and the natural frequency of a second order system. And when we have the time response, we need to find the settling time, peak time, percent overshoot, and rise time for an underdamped second order system. I mean, the second order system, we can divide it into underdamped, overdamped, and critically damped second order system. So for the underdamped system, we need to find the settling time, peak time, percent overshoot, and rise time. We need to approximate, or we need to know how to approximate higher order systems and the systems with zeros as first and second order systems. This is very, very important because most of the design techniques are developed for second order system. So it's very important to know how to approximate higher order systems as a second order system. We need to describe the effects of nonlinearities on the system time response. We need to find the time response from steady space representation. So you can say that it's also, in this unit, chapter 4, we try to cover many things. So the main idea again, because now we need to just cover things from chapter 2, chapter 3, and finally chapter 4. We need to have system representation. We can represent a system as a transfer function or in steady space. Transfer function we covered it in chapter 2, and the steady space representation we covered it in chapter 3. Now in chapter 4, we need to analyze the time response. And once we analyze the time response, we will be able to characterize the performance of the system. And in this case, we will be able to design a controller to achieve those design requirements. So the main idea here, we are starting by system representation, and in this system representation, we can represent the system by transfer function, and we did that in chapter 2, or in the form of a steady space representation, which is very beautiful, and we did that in chapter 3. In chapter 4, we will analyze the time response of your system, and by analyzing the time response, we will characterize the time response, and based on this, we will have some design requirements. We will get it maybe from the end users, for example. Based on this, we will try to design a controller which will be able to achieve those design requirements. So we need to start by analyzing the time response. We will have some design requirements. We will design a controller to achieve those design requirements. And to ensure that we are able to achieve those, we need to go back again for the analysis to ensure that we are able to achieve those design requirements. So in chapter 3, after getting the mathematical representation of a system, it is analyzed for its transient and steady state response to see if these characteristics can give us the desired response. If not, we need to design a controller to help the system to behave as it is required. So you are starting by a system. The system can be represented in the frequency domain by transfer function, or in time domain by steady space representation, chapter 2 and chapter 3. After that, we will analyze the time response. If this time response does not fulfill your requirements, so you have maybe a settling time, but you are not happy with the settling time, you need to speed up the response a little bit. So in this case, we will go into the controller design. We will design a controller. We will apply this controller to our system, and we will analyze one more time to ensure that we are able to achieve those design requirements. What are the poles, zeros, and the system response? So the output response of a system, which is a differential equation, and we agreed that this differential equation is a summation of two components. The first component, it is a forced response, right? And this forced response, we call it steady state response, because we will get this forced response after the transient response. So when we are in a steady state, we can say that now we have the forced component of our differential equation. Plus natural response. This natural response, it's called also unforced response. So we have forced response and unforced response. So the forced response, it's due to the input. Unforced response, it's due to the natural response or the system dynamics. The unforced response, it should decay over time. Maybe after in fact, it constitutes the transient response. It is the main component of the transient response. So this unforced component or unforced response, it should decay out after the transient response. In a steady state, we should have only the forced component or the forced response. So if we need to plot it, it will be something like this one. We can have the response like this one. This is t. This is maybe y of t. So we get this transient response, and after that we will be in a steady state. So the part here in a steady state, we call it forced component, right? And the response here in the transient phase, we call it natural component or natural response or unforced response. So this one is unforced, but in steady state we call it forced component, and this forced component, it's due to the input because we provide a desired input to the system and we want our system to follow it. So this is a forced component. In PDE, it's partial differential equation, forced response. I mean, in mathematics, in fact, this forced component, we call it a particular solution, while natural response, we call it homogeneous solution. System response can be obtained by solving its differential equation. We did that in chapter 2. So when we have a complex differential equation and we need to solve it, one way for solving it, in fact, is to solve it in frequency response. So we apply Laplace transform, we simplify, we provide the input. So maybe the transfer function will be g of s equal y of s divided by r of s. We need to get y of s in one side. So we need to substitute r of s for step input or for ramp, for example, and we will use partial fraction expansion, and we will simplify our transfer function as a summation of simpler components, and we will go to the Laplace transform table, inverse Laplace transform table, and we will try to find expressions in time domain representing this one. So we will convert our solution into time domain, and this one will be our solution. And our solution will consist of two parts. One part is forced response, and the other part is unforced response. Forced response, it's due to the input. Unforced response or natural response or homogeneous solution, for example, this is due to the system dynamics. And this part should decay over time. So we should have exponential negative or exponential negative multiplied by sinusoidal, right? When your system is first order, it will be only exponential negative, right? When it is a second order system, it will be exponential multiplied by sinusoidal. So the sinusoidal, it will constitute this overshoot and undershoot, and after that the response will decay, right? So this one, in fact, it will be exponential multiplied by sinusoidal component. So a rapid approach, your system response can be obtained by solving its differential equation or taking its inverse Laplace transform. I mean, this process, we tried it in chapter 2, right, and in chapter 3, and it's time consuming because it takes time. Maybe one better way for doing this is to use a static space representation, and we will be able to get the same response. Because in a static space representation, it's a set of first order differential equation, and we know how to implement it in a for loop and try to obtain our response. So a rapid approach which can yield results in minimum time is by inspecting the relationship between poles and zeros in one side and the time response in the other side. So there are some qualitative approach which can be used for obtaining the time response. Poles and zeros of transfer function, they in fact constitute something called the characteristic equation, which is the denominator of the transfer function. I mean the transfer function g of s, it's two parts, right? So we have here one part and one part here. The denominator here, we call it characteristic polynomial, right? We call it characteristic equation of the transfer function. When you the poles, in fact, the poles are the roots of this characteristic equation. So characteristic equation is the denominator of the transfer function. Poles of the transfer function are the values of the Laplace transform values s that causes the transfer function to become infinite, which are the roots of the denominator, right? So we try to factorize the characteristic equation, which is the denominator of the transfer function, equate it to 0, and find its roots. Those roots are the poles. The zeros on the other side of the transfer function are the values of the Laplace transform variable s, which causes the transfer function to become 0. So in fact, the zeros, those are the values of s, which will make g of s equal 0. If you want g of s to be equal 0, you need to set the numerator equal 0, right? So we need to get the roots of that part. If you want to get the poles will be the values of the Laplace transform variable s, which will make g of s equal infinity, right? If you want to make g of s equal infinity, in this case, we need to set the denominator equal 0. So it should be something divided by 0. When it is something divided by 0, it will be infinity. Poles, so the poles produces infinite output. So the output will be infinite, it will be infinity. And the zeros, the system will produce 0 output. So if you substitute those zeros to the transfer function here will be 0. Here transfer function will be infinity. We know why it will be infinity, because it will be something divided by 0, right? You cannot produce infinite voltage with any electronics, so it means that the output will be unbounded in theory and saturated at the highest maybe possible value in practice. Because we cannot get infinite output, right? We cannot get infinite output from my system at the poles, at the system poles. We cannot get infinite output, right? So it means maybe your system or your output will be unbounded, but when it is unbounded, your system will be unstable. But it could be saturated because we can reach the highest possible value of this actuator. For example, you have an actuator. It's like your car engine, for example. You have maximum speed. You cannot go beyond it. So in this case, we will go to the infinite or infinity. So the output will be infinite. It will be like this one. We need to have an example. We solved this example before. It's LC circuit. We need to find, we need to solve it, right? So one way for solving, we need to get system poles and zeros of this LC circuit, right? So this one we call it LC circuit. It consists of inductance and the capacitance, right? So we have here inductance and a capacitor here. So one way, in fact, for getting the transfer function of this one is to try to get the impedance. The impedance of L, it will be SL. Impedance of L, it will be SL. Impedance of C, it will be 1 divided by CS, right? It will be like this one. So the impedance of L, we need to replace it with the impedance because we need to get the transfer function. So we need to replace each component with its impedance. Impedance of L, it will be SL. Impedance of C, it will be 1 divided by CS. Total impedance, because this is, two branches in parallel. So the impedance, it will be this one multiplied by this one, divided by the summation, because those are parallel branches. We need to get the overall impedance. So the overall impedance, Z, it will be ZL multiplied by ZC, divided by ZL by ZC. So just substitute values. So it will be LS multiplied by 1 divided by CS. So S will cancel S, so it will be L divided by C, right? Divided here by LS plus 1 divided by CS, just multiplied by CS. When you multiply it by CS, this one will be LCS square plus 1, and this one will be LS. So as you can see here, it's second order system, because the order here, the order of the part is 2, which means we have 2 poles. This one, it's second order system. And we have here 1, 0, right? So we have here 1, 0, we have here 2 poles, correct? How can we find the zeros? We need to substitute S at S equals 0. Z total, this one it's a Z total, it should be equal 0, right? When you substitute here S equals 0, when we set S equals 0, what will happen for Z total? So Z total, in fact, it will be L multiplied by 0, it will be 0, divided by LC multiplied by S squared, which will be 0 plus 1. So it will be 0 divided by 1, it will be 0. And this is the definition of the zeros, right? So in this case, we can say that at S equals 0, we will have a 0, correct? Okay. Now we need to substitute, we need to have that part here, denominator here equal 0. So we will set LC S squared plus 1 equal 0. So in this case, S squared will be minus 1 divided by LC. So in this case, what will be the value of S? So S will be, because this is the square root, right? It will be plus minus square root of minus 1 divided by LC, right? Square root of minus 1, it's a J, right? Square root of minus 1 equal complex number called J. So this will be plus minus J multiplied by square root 1 divided by LC, right? If you want to make it more beautiful, so it will be plus minus J divided by square root LC. Because the square root of 1 equal 1, and the square root of LC, it will be LC. So it will be like this one. So now, in fact, if we need to put it in this S plane, so it will be something like this one. For L and C value, maybe we will have 1 pole here and 1 0 here, right? No, it's complex. In fact, it's a plus minus, so it will be something here and something here, right? Not that one, because this is a complex plane. So anyway, when you substitute this value in this equivalent or overall impedance, when you substitute S squared equals this value, this one will be 1 minus 1 plus 1, so it will be 0. So in this case, Z total will be infinity, which means we have poles. So when transfer function equals 0, we will get the system zeros, and when the transfer function equals infinity, we will get the poles. So poles of the transfer function is a characteristic of the system, and it's connected with the natural response of the system, while the zeros represent the forced response. Forced response means this is the force variable or the input. Forced component, it's due to the input. We try to force the system to follow something. So we can say that, okay, poles are connected with the system dynamics, but zeros are connected with the input, right? It's the forced variable or the input. Poles describes the main dynamics. They are the eigenvalue. I mean, they are representing the main dynamics of your system. They are the eigenvalues of the matrix of the dynamics, which is a system matrix A in status-based representation. So in status-based representation, we have x dot equal ex plus bu, and the output y equal cx plus du. In fact, the eigenvalue of A, of system matrix A, it will be my poles. So the poles will describe the main dynamics, and they are the eigenvalues of the system matrix A. All of them have to be in a stable region in order to have a system stable. I mean, all of them must be negative, right? If you want your system to be stable, because if we need to plot it in this S plane, it must be plotted here in the left-hand side. We have here left-hand side, right-hand side. All of them must be here, right? Your system your poles must be in this for your system to be stable. And it's important because when you use inverse Laplace transform, this one will generate exponential negative. Otherwise, if it is here in the right-hand side, it will be exponential positive. And when you have exponential positive in your time response, it will be unbounded, correct? Your system will just go to infinity. The output will go to infinity as time goes to infinity. So your system will be unstable. So here your system will be unstable. Your system here will be stable. If you have a single one on the right-hand side, your system will be unstable. So it must be in the stable region. In order to have a system stable, all of them have to be reallocated in prescribed position via feedback to have a closed loop prescribed stability degree, which cannot be achieved in open loop. If your system is unstable, or maybe it's stable, but you cannot achieve the desired performance which you want. So in this case, we can consider something called pool reallocation. We need to reallocate our pools to some locations which will achieve our performance. We can do this if we will use feedback closed loop system, right? We cannot achieve this if you will control your system in open loop, because when you are controlling your system in open loop, you just provide a control signal to your system, but you can't control the system dynamics. So we can design a controller, and this controller, when we close the loop, we can design a controller which will try to reallocate our pools to some specific locations. Pools on those locations will achieve the performance which we want to achieve. The zeros will impact the relative stability. So how far or close the frequency response is from the critical stability, which is this point -1 and G0 in the Nyquist plot, and they can then improve or worsen the transient response. Those zeros will impact the transient response. It can improve it or it can enhance it. So they have also the system zeros also has also some impact on the stability or the overall performance of your system. Let us take it step by step. You have poles and zeros of first order system. You have the system. It's first order. Transfer function of this system, and we will call it G of S. It will be S plus 2 divided S plus 5. If you need to get the system zeros, so we need to set that part. We need to set G of S equals 0. If you want to set G of S equals 0, we need to set S plus 2 equal 0. So in this case, S equal -2. So in this case, we will have a 0 at minus. This one is a 0. We represent it by a circle. This one will be a 0. Okay, if you want to get the system poles, we need to set G of S equal infinity. And you can achieve this by setting that part equal 0. So S plus 5 equals 0. So S equal -5. So this one will be a pole. This one is 0. So S -5, so it will be here. S -5, and it's by cross, by X. So this is how we will put it in this S plane. So this one will be a pole. So how it will look like. So as you can see here in this S plane, this is the real axis. This one, we call it real axis. This one, it's imaginary axis, right? And as you can see here, it has also a left-hand side and right-hand side. Your system poles and zeros must be located in the left-hand side if you want to have a stable response. So the system, in fact, it's stable. So you can check stability quickly by just looking into pole zero locations in the S plane. So as you can see here, all poles and zeros are located in the left-hand side, and as a result of this, our performance or our system will be stable. Yes. So if you want to get those pole zeros of the first order system, you have a transfer function. We have a pole exists at S -5 and a 0 exists at -2. These values are plotted in the complex S plane. We will need to plot it in this complex S plane using an X for the pole. We represent poles by X and a circle for the 0. So we will represent a pole by an X, and we will represent a 0 by a circle to show the impact or purpose of poles and zeros. Let us find the unit step response of the system. Multiply the transfer function by the step function. I mean, this is my system G of S, and this is the block diagram representing it. and we need to check the performance or the output for step input. Now we have G of S. It's S plus 2 divided by S plus 5. The input is R of S and the output is C of S. So if we need to get G of S, so G of S will be the output divided by the input, C of S divided by R of S, equal transfer function, which is plus 2 divided by S plus 5. If you need to get the response, C of S, so do cross multiplication. So in this case, we can say that, okay, C of S equal my transfer function, which is S plus 2 divided S plus 5 multiplied by R of S. For step input, R of T will be 1. When R of T equal 1, so R of S will be 1 divided by S. So in this case, we can say that C of S will be S plus 2 divided by S multiplied by S plus 5. Use partial fraction expansion. So it will be A divided by S plus B divided by S plus 5. To get A, just multiply by S and substitute S equals 0. So it will be 2 divided by 5. So it will be 2 divided by 5 divided by S. And we have here S plus 5. To get B, multiply both sides here by S plus 5 and substitute S equal minus 5. So it will be minus 5 plus 2. It will be minus 3 divided by minus 5. So it will be also plus 3 divided by 5. So it will be like this one. Apply inverse Laplace transform. So C of T will be 2 divided by 5 plus 3 divided by 5 exponential minus 5t, right? So this is very important. So as you can see here now, if when you look to this system ball, when you look into the system ball, this ball in the complex S plane, it was located at minus 5, here at minus 5, in the left-hand side. If it is, when it is in the left-hand side, it will generate exponential minus 5t. So this is a natural component, and this natural component, it will decay over time. So if you can substitute as t equal infinity, C of t will be what? Or C infinity will be 1. It will be only 2 divided by 5 because that part will be 0, right? So it will be 2 divided by 5. 2 divided by 5, this is the forced component. So now we can get the response, and you can go to MATLAB or Python code and try to plot your response. So, right? And as you can see here, we have only here exponential part. This one, it's exponential part. So if in the exam, for example, I told you how the response of the system will look like, is it something like this one, or is it something like this one? Which one you will choose? A or B, for example, for this response? No, you should select A, because here in this example, we don't have, it's not second order system, it's first order system. We have only this exponential part, and the exponential part will behave like that part, not like that, because we don't have any sinusoidal component here. We don't have sine omega t or cosine omega t, so we will not be able to get this overshoot and undershoot from this first order system, and the response in this case will look like the response in figure A. So step response when ut equal 1, when the input equal 1, which is step. So in S domain, it will be 1 divided by S. And we call it input bool, correct? Because the transfer function, in fact, when we try to find C of S, so C of S will be something like this one. It will be S plus 2 divided by S plus S plus 5. So in fact, this input generated something called input bool, right? Input bool. It's from the input. It's not from the system dynamics. I mean, you got this component here because of the input, because of the step input, right? Not because of the system dynamics. System dynamics here are represented by S plus 2 divided by S plus 5, not by S. This S, we got S because of the input, because of the step input, right? So this input bool, it's S equals 0, right? Just, I mean, when we try to find this input bool, so it's S equals 0. So it will be cross at the origin. This in the complex S plane, it will be something like that part here. It will be here, because here S equals 0. And also we have another bool, and in this case, we will call it system bool. This one will be, this one input bool, this one will be system bool. we will have a system pool at s equal -5. So it will be that part. So we have input pool and we have a system pool. Still, we have here a 0 at s -2, and it will be system 0. So we'll have a system 0 -2. When you look into the output response in S domain, C of S will be 2 after applying partial fraction expression. So it will be 2 divided by 5 divided by S plus 3 divided by 5 divided by S plus 5. So in fact, we have two components. One component is generated by the input pool, right? This one is generated by the input pool, and this component is generated by the system pool. The one which is generated by the system pool, it will decay because this is a natural component. It's connected with the dynamics. But the one which is generated by the input pool, it's because of the input. So it will generate this forced component. This one will generate forced component. This one will generate natural response or unforced response. So the forced response equal a constant value, and it's due to the input pool. Natural response, it's a submission of exponential terms, and it's due to system pools on the real axis, right? And in fact, this system 0, it will impact the amplitude, right? This system 0, in fact, it's like a gain, so it will impact this. It will impact both of them, but it will impact only the gain of the response. So the system here in figure 4. In this figure, we have the system showing input and output. We have pole 0 plot of the system. This is, we call it pole 0 plot of the system, and evolution of a system response. Follow arrows to see the evolution of the response component generated by poles and zeros. So you can just understand that we have this forced component. The forced component, it will be generated due to the input pool, and the natural response, it will be generated due to the system pool. We have input pool, system pool. So the conclusion, a pool of the input function, it will generate the form of the forced response. So the forced response will be generated due to the input pool. And it's a pool at the origin, which is generated by the step function at the input. We will have something here in the origin, right? We will get something here. We call it input pool, right? This input pool, in fact, it's S equal 0, and it's generated because of the input. And this one will generate the forced component. A pool of the transfer function, it will generate the form of the natural response. So this one will generate the natural response. This one, it will pool at minus alpha. It will generate a response which is k multiplied by exponential minus alpha t. So if you have this pool in the right-hand side, right? So it will be plus alpha here, right? If you have something here which is plus alpha, so in this case, this one will generate a k exponential plus alpha t. And in this case, this one will be unbounded. So your system will be unstable. So if you have even a single pool in the right-hand side, this one will make your system unstable. So we don't care. If you have if you have a system which is fifth order and you have 4 pools located in the left-hand side and you have only one located in the right-hand side, this one in the right-hand side, it will make your system unstable. Because it will generate this positive exponential part. It will generate k multiplied by exponential alpha t, for example, and this one will be unbounded. So as t equal infinity, that part will go to infinity. So your response will be unbounded. So a pool of the transfer function, it will generate the form of the natural response, which is at -5 here in this example. It will generate this component, which is exponential -5t. A pool on the real axis, it will generate an exponential response of the form of e exponential minus alpha t, where minus alpha is the pool location on the real axis. The further to the left a pool is on the negative real axis, the faster the exponential transient response will decay to 0, right? So for example, if you have something at -5 and something at -10 or -100, exponential -100 t, for example. So which one will decay first? So the one which will decay first, it's the one which is far from the G omega axis. So the one as far as you are from the G omega axis, the faster that component will decay, right? The faster the exponential transient response will decay to zero. So we can say that, okay, if you have two systems and you have some poles which are closer to the G omega axis here, maybe your system will be stable, but it's not be very good in fact, because your system will be you will stay longer time in the transient response. It will take longer time to decay. But if you have poles which are far from the G omega axis, so in this case the response of your system will be much quicker, right? Because that part will decay faster, right? That part will decay faster. Zeros, zeros and the poles, it will generate the amplitude for both the forced and the natural response. So it's just, I want to go back to this slide here. I mean, we have got here 2 divided by 5. And I mean, this amplitude, it will be generated by both the poles and the zeros, right? That part, 2 divided by 5, 3 divided by 5. So in fact, it's common contribution between both poles, system poles and zeros. Yes. Partial fraction expansion, again, we did that in chapter 2 and in chapter 3, but it's just revision. And as I told you, we do revision from time to time. Partial fraction expansion, which called partial fraction decomposition, also is performed whenever we want to represent a complicated fraction. We need to represent a complicated fraction as a sum of simpler fractions. So we have a transfer function, and this transfer function, it's a numerator divided by the denominator, and it's complex fraction, and we need to simplify it as a sum of simpler fractions. And when it is a sum of simpler fractions, it's easy to go to Laplace transform table and try to apply Laplace transform, inverse Laplace transform to get the solution of your differential equation. So if you have complex differential equation, you just need to put it in frequency domain by applying Laplace transform, and after that you apply a partial fraction expansion to convert it into a sum of simpler fractions. Then apply inverse Laplace transform to get your solution as we did here. So for this system, which is simple, so we can say that, okay, this is complex fraction, and we will apply partial fraction expansion here to convert it into a sum of simpler fractions. This one is second order. Now it's summation of first order fractions. This one is first order. This one is first order because the order here is 1, right? So we can say that it's a summation of simpler fractions. So it will be easy for us to apply inverse Laplace transform and get this form. This occurs to find inverse Laplace transform of a complicated function if you have very complicated partial differential equation. So in this case, we can just apply Laplace transform and then partial fraction expansion to convert this complex fraction into a sum of simpler fractions, and then apply inverse Laplace transform to get your response in time domain. So the order of NS must be less than the order of this one, usually in control systems, the order of this one should be less than the order of this one. If not, you need to apply long division. We applied it in chapter 2, if you can remember. So the order of N of S must be less than the order of D of S. If not, you need to apply long division. This is Laplace transform table. We covered it before. So, maybe the most common stuff which we will use in this course, it will be that one. So if you have for step input, for example, so the Laplace transform it will be 1 divided by S. That part also, it's maybe the most part which we will use. Exponential alpha t or at, it will be 1 divided by S minus a, right? This one. So Laplace transform, you will go into from this one to this one. And the inverse Laplace transform, you go in the opposite direction. Maybe also that part is important. When it's t, so it will be 1 divided by s squared. So for t, it should be converted into 1 divided by s squared. So we can say that, okay, when the input is 1, it will be 1 divided by s. When it's t, it will be 1 divided by s squared, and so on, right? When it's also maybe t multiplied by exponential at, t exponential at, so it will be something like this one, 1 divided by s minus a squared. So it will be something like this. And of course, we have the cosine, sine, and so on. Those those functions also are very important. Now we need to have an example. We did that before also, just to remember, it's a revision. As an example of partial fraction expansion, you have this function, and it's the order of that part is 1, the order of that part is 3. So the order of that part is less than the order of that part. It's complex fraction. So we need to represent it as a summation as a sum of simple fractions. How can we do this? You need to factorize that part. So first we can see here we have 10s, 7s squared, s cubed. So we need to take s as a common factor. So that part will be s multiplied by s squared plus 7s plus 10. And the 10, in fact, it's 2 times 5. So this one will be s times s plus 2 multiplied by s plus 5. So it will be like this one. If you want to go back again, so s times s, it will be s squared. S times s, 2s plus 5s, it will be 7s. And the 2 times 5, it's 10. Right? So now we are correct. So we will write it as a summation of simple fractions. So it will be a divided by s plus b, for example, or a2 divided by s plus 2 plus a3 divided by s plus 5. And after that, we will use the limit to find the value of a1, a2, a3. What will be the value of a1? Multiply here by s, so this one will be cancelled. And substitute s equals 0, so it will be 3 divided by 10. So a1, it will be 3 divided by 10. If you want to get a2, multiply by s plus 2, and set s equal minus 2. So it will be minus 2 plus 3, it will be 1 divided minus 2, multiplied by minus 2 plus 5, it will be 3. So it will be minus 1 divided by 6. So in fact, a2 will be minus 1 divided by 6. For a3, multiply by s plus 5. So this one will be cancelled. And the set s equal minus 5. So it will be minus 5 plus 3. It will be minus 2. Divided by minus 5 multiplied by minus 3. Correct? So it will be in fact 2 minus, it will be minus 2 divided by 15, right? So it will be a3, it will be minus 2 divided by 15. So now we can find the value of a1, a2, and a3. So as you can see here, a1 will be 3 divided by 10. Is it correct? Yes, 3 divided by 10. a2, it will be 1 minus divided by 6. 1 minus divided by 6. This is correct, right? So this one, it's okay. 1 divided minus 1 divided by 6. And a3, it will be minus 2 divided by 15. Minus 2 divided by 15. This is correct. So now we can get those a1, a2, and a3. So now to get your final solution, so just write. So it will be write it like this one. So it will be 0.3 divided by s minus 1 divided. So just write it in this way and apply inverse Laplace transform. So it will be minus 3. This one, it will generate minus 3. This one, it will be minus 1 divided by 6 exponential 2. It will be minus 2t, right? Minus 2 divided by 15 exponential minus 5t. So it will be like this one. And as you can see here, we have a forced component. This one we call it forced component or forced response. And that part will be natural component. Natural component, correct? So now we can get the response, f of t, right? We can get f of t. We have here, in fact, if we need to have this pole zero plot, we need to do our S-plane, complex S-plane. This one will be real axis. This one will be g omega axis or imaginary axis. We will have pole at minus 2, right? And minus 5, minus 2. And also we have here a 0 at minus 3. It will be minus 3 here. So as you can see here, the exponential part, which is generated from -5, it will decay faster than this one, right? It will decay faster. So that part, it will decay faster than that part. So when you go far away from the g omega axis, your system will be faster, right? Your system will be, because the exponential part, it will decay faster, which means your system will be much faster, correct? So we can also have equation in that part. So we have a response like this one, and maybe something like this one, and another response which will be like this one. So which one? Is it this one or this one? According to your pole locations. So in fact, as you can see here, we try to revise partial fraction expansion from chapter 2, right? So here also, it's another example which we solved, chapter 2, page 37, where the order of n of s is greater than the order of d of s. So the order here is higher than the order here. And in this case, we need to divide n of s by d of s. Using long division, we did that in chapter 2, until the result has a remainder whose numerator is of order less than that of the denominator. So we have this example. So as you can see here, the order of that part is 3, and the order of that part is 2. So in this case, we cannot use partial fraction expansion. First, we need to use long division. We need to divide that part by that part until the order of the denominator is less than or equal to the numerator. So we will use this long division. We need to divide that part by that part. So we will have this long division, and I explained this long division before, but we can do it one more time until we have a remainder. So we will divide s cubed by s squared. So you will get s cubed divided by s squared, it will be s. Multiply s by that part, so it will be s times s squared, it will be s cubed. S times s, it will be s squared. S times 5, it will be 5s. Subtract. So this one, s cubed minus s cubed, it will be 0. 2s squared minus s squared, it will be s squared. 6s minus 5s, it will be s and 7. Now this order is still higher. We don't have a remainder. We will do a division one more time. So s squared divided by s squared, you will get 1. Multiply, so it will be s squared plus s plus 5. Subtract. This one will be 0. This one will be 0 plus 2. So now we have the remainder. So we can say that f of s will be s plus 1 plus 2 divided by that part. So now we are happy with that part, because now we can just apply here partial fraction expansion if it is possible, and try to simplify it as a sum of simpler fractions. But that part, in fact, can we factorize that part? It's 5. It should be 5 times 1. So it's impossible. We need to keep that part as it is. So there are 3 cases in chapter 2. First case, roots of denominator of f of s are real and distinct, which we did in fact, and this one. So there are 3 cases. We need to do it, right? In chapter 2. So you need to go to chapter 2 from page 37 to 44. So you can revise those 3 cases. When roots of denominator are real and distinct, roots are real and repeated, right? We solved it. Roots of f of s are complex and imaginary. So just focus at least on 1 and 2, for example, right? So we did this long division, and after that we will try to apply Laplace transform so we can get f of t, because the most important for us here is to get f of t. So we have here another example. Okay. It's 57 minutes. Maybe we can finish this example, and after that we can go to first order system. So we can stop here. So we will finish example 4.1, and after that we will stop here. So you need to evaluate your system response using poles. So you have a problem here. Try to find. You have this problem. You have this system. C of s equal g of s multiplied by O of s, right? This is my transfer function g of s. that part. So we need to find C of t. First, we need to find C of t. Specify the forced and the natural part of the solution. We need to find what is the forced component, what is the natural part of your solution. So first, we need to get C of S. So just remember, your transfer function G of S equal C of S output divided by input R of S. We need to get C of S. So cross multiply. So C of S will be R of S multiplied by G of S. And for R of S equal 1 of S, so it will be S divided by 3 divided by S multiplied by S plus 2, S plus 4, S plus 5. If we need to draw this system, I mean, in this S plane, it will be something like this one, right? We will have here input pole at S equals 0. We will have something at -2. It's a system pole, something at -4, and something at -5. Those are my system pools. This one it's input pool. Remember, because in fact we got this one because of the input, so we call it input pool. But this one it's system pool. This one is system pool. Those one are system pools. We look into the zeros. We have a 0 at -3, so we'll get something here at -3. It should be a circle, right? So it will be X when it's pool, and it will be a circle when it's a 0. This one it's system 0. This one it's delta, or this one it's G omega, right? So this is my S plane. We call it complex S plane. And when you look into this one, okay, my system is stable, right? Because all my system poles are located in the left-hand side of the S plane. Left-hand side, and this is right-hand side. Right-hand side is clean. We don't have any poles in the right-hand side. If you have anything in the right-hand side, it will generate this exponential positive. So it will be unbounded. But when it is in left-hand side, it will generate all time E negative alpha t. So anyway, when this one is negative, this one will decay, right? If you want to solve this one, by inspection, each system pole generates an exponential component as part of the natural response. So the input pole generates the forced response. So we can just by inspection, we will get K1 divided by S, K2 divided by S plus 2, K3 partial fraction expansion, K3 divided by S plus 4, K4 divided by S plus 5. This one will be the forced component. It will generate the forced component because it's due to the input. This one will be unforced component or natural response, and it's generated due to your system pools. Take inverse Laplace transform. So this one will be K1 plus K2 exponential minus 2t, K3 exponential minus 4t, K4 exponential minus 5t. So your total response will be forced component plus natural component. This one will be the natural component. This one will be the forced component. If you want to get values for K1, K2, K3, K4, you can get it, right? So for example, if we need to find the K1, multiply here by S and set S equal 0. So in fact, here K1 equal, it will be 3 divided by 2 multiplied by 4 multiplied by 5. 2 multiplied by 4, it's 8. So it will be 3 divided by 40, right? So it will be like this. And you can get K2, K3, K4 in the same way. Yeah, that's a 3. In fact, I solved it here for you. K1 is 3 divided by 40. If you want to get K2, so you just also take the limit of S plus 2 multiplied by C of S as S go to minus 2. So it will be minus 1 divided by 12. If you want to get K3, so we need to multiply C of S by S plus 4 and substitute S equal minus 4. So it will be minus 1 divided by 8. K4, it will be S plus 5 multiplied by C of S as S takes the limit as S go to minus 5. So it will be 2 divided by 15. So pole 0 blocks, as we did, all poles are in the left-hand side of the S plane, and therefore the system is stable. Your system is stable because we have all poles are located in the left-hand side of your S plane. We have this right-hand side, it's clean, so don't have any problem. And of course, we have here also something at 0. which is this one, we call it input pool. Input pool. It will be all time at 0. So pools of the input function determines the forced response. Pool of the input. So the pool or input pools determines the forced response, while system pools, which is pools on real axis, it will determine the natural response or the exponential terms. We have exercise 4.1. You have system which has this transfer function. Write by inspection the output CFT by inspection, which means you don't need to solve it in details. So by inspection, when we look into this one, by inspection, C of T will be for input unit step, for the input equal unit step. So in this case, R of T equal 1. So R of S equal 1 divided by S. So you can just say that, okay, output is C of T or C of S will be G of S multiplied by R of S. So it will be 10 multiplied by S plus 4 plus S plus 6 divided by S multiplied by S plus 1 multiplied by S plus 7, S plus 8, S plus 10. By inspection, C of T will be K or coefficient multiplied by S, right? So in time domain, it will be just maybe constant called A, for example, plus this one will generate P exponential minus T, plus this one will generate coefficient C exponential minus 7T, plus D, this part will be exponential minus 8, plus that part, it will be, for example, E exponential minus 3T by inspection, right? So it will be like this one. I asked you here to just continue solving this problem using partial fraction expansion and try to find A, B, C, D, and E, and also draw your pole 0 plot. This one. When you draw this pole 0 plot, it will be something like this one. It will be something like this one. This is delta, this is G omega, this is my complex S plane. So we will get something at the origin, which is system pool, at -1, at -7 here, yes, -7, -8, -10. And the zeros, you have one at -4 and -6, -4 and -6. Maybe -6 here and -4 here, right? It will be -6, -4. So it will look like this one. So it's easy, right? And as you can see here, your right-hand side is okay, clean. All your poles and zeros are located in the left-hand side, which means your system is stable. Okay, so we will stop here. So because now it's more than 1 hour, 1 hour and 5 minutes, we will finish here and we will meet again in the second part of this lecture. Thank you very much.